Okay, class, welcome to the first lecture in the Intro to Proofs class. So we're going to start off talking about something called statements. And this is what math is all about. So we're going to leave behind all the baby stuff that you've learned in previous math classes, and we're going to start doing real math here. And what it's all about is proving statements. Now, we're going to talk about statements today. We're not going to talk much about proving. So I'm going to put proving in quotes. So I'm not going to tell you exactly what proving is yet. Just know that when we say that we prove something in math, we are very precise about what that means. It's not like when you prove your relatives wrong on Facebook by giving them an article to read or something like that. It's much more precise. Okay, but today we're talking about statements. So what the heck is a statement? A statement is something very precise in math, and because I'm defining it, I'm going to underline it. It's a sentence, and this can be a sentence in English or a mathy sentence, which you'll see lots of, but it's a sentence which is either true or false. And there's no question about which one it is. You might not know which one it is, but there's no question that it is one or the other. There's no ambiguity, so it can't be both. It can't be sometimes true, sometimes false. It just is true or false. Now, when we write statements in English, it is going to seem ambiguous, but that's just because of English. That's not because of math. So when I write examples of statements down in English, I'm going to try to be extra careful to make sure it's something that's either true or false and not ambiguous at all. Okay, so whenever I write down an example, I'm going to write this little EX thing because I'm too lazy to write the whole word every time. And this is going to show up a lot in this class. Okay, so here I'm giving you an example of a statement. And I'll put it in quotes to separate the statement from the explanation, but that's not good. That's not English. It rained in Los Angeles on June 1st. So this is a statement because it's either true or false. It happened or it didn't happen. There's no ambiguity about that. It's not a very mathy statement. And I want to compare that to something a bit more tricky. If I just say it is raining, well, and it sort of depends on who says it, and it's kind of annoying to work with. So a lot of people would say that that is a statement also, because it either is raining, true, or it is not raining, false. But when I'm dealing with examples in English, I'm going to try to be less ambiguous, because to me that's still a bit ambiguous. Okay, that's why math is so nice. There's no ambiguity. Okay, so let's do a mathy statement. So that's an example of a statement. Here's another one. There exists whole numbers A, B, and C such that A squared plus B squared equals C squared. So this is a very mathy sentence. You'll see the phrase there exists and such that quite a lot in this class. But what I want to focus on right now is the fact that the entire thing is the statement, okay? So you can't just look at one piece or another. You can't just look at the equation that you see, the A squared plus B squared equals C squared. You have to look at the whole thing. So this is a statement, and the whole thing is the statement. So it's a statement because either there do exist whole numbers a, b, and c such that this equation holds, or it's false and there do not exist whole numbers that have this property. So it's got to be one or the other. We might not know which one it is right now, but it is true or false, and there's no ambiguity there. That's the nice part about math statements. So just as important as examples are non-examples when you're trying to understand something new. So here is something which is not a statement. If I just write a squared plus b squared equals c squared, well, that's not a statement. Because whether it's true or false changes depending on a, b, and c. So it's not just true or false. And so you can think about it by saying like an equation is not a statement. So the trueness or the falseness depends on a, b, and c. So it's not just true, it's not just false. So that's why it's important to read statements as a whole. So this guy involves the same equation, but it is a statement because it's saying something about the equation. It's saying that there exist solutions to that equation. This is just saying an equation, so it's not a statement because it could be true, it could be false, it just depends on A, B, and C. So what about something like this? Let's do an English example. So coconut milk is the best milk. So I hope that this one is very clearly not a statement because it's an opinion. It's an opinion that I hold. Try coconut milk if you haven't, it's the best milk. But in any case, it's not true or false. So it's not a statement. Okay. Here's another non-example that's more tricky. X is an even number. Is not a statement. It's very similar to the equation that I wrote up here being not a statement, and it's because it depends on X. So the answer changes whether it's true or false depending on what X is. So if I want to compare to something that is a statement, so if I wrote an actual number like 6 is an even number, that would be a statement. And I can also write 7 is an even number, is also another one. Notice I'm not caring about whether it's true or false. I hope you can tell that one of these is true and one of these is false. The point is that they are true or false. And there's no ambiguity. Okay, so that's why those two are statements, but if I just said X is an even number, and I don't say anything else, that's not a statement, because it depends on X. It can change. So although I said equations are not statements in general, you might think that this next example is an equation, but that's just a very subtle difference. So this is an example of a statement. If I write 5 equals 3, you might say, but that's an equation. But it's an equation involving two numbers that have already been determined. So it is something that is true or false. So this is a statement. And I hope you can believe me, it's false. And I can do other little things like this. So 5 is bigger than 2. That's what that symbol means. This is another statement, even though it doesn't have any words in it, just because it's a relationship between two numbers that is true or false. In this case, it's true. But if I do something like x is bigger than 2, and it's not a statement anymore, because it depends on x. I can do something like this. 7 does not equal 10. This is a statement, and it's true, because 7 does not equal 10. Let's see, what other examples can I think of? How about this one? So those are things that are sort of true and false, and you can see right away whether they're true or false just by looking at it. But in math, we care about statements that are more complicated, that are not obviously true or false. So we'll get to something like that in a second. Maybe this one you might think is not true or false, and you might not know, or sorry, this one you might think is true or false, and you might be wrong. So let me try to trick you. For any triangle with sides A, B, and C, A squared plus B squared equals C squared. So this is a statement because it's either true or false, and which one do you think it is? So you may think it's true because you're focusing too much on the equation. You think, aha, I know that equation, it's the Pythagorean theorem. But in this situation, the equation does not hold for the things that it's supposed to hold for in the statement. So it's actually false. We'll get into that more later on. But for now, we're just analyzing if it is a statement or not. It is. Because either this is true for every triangle or it's not. Okay, so one more non-example. Well, I'll just put the non in the example. Is something like this. Solve 3x plus 5 is 2. So this is not a statement either, because it's not something that's true or false. Instead, it's a command. Okay, so those are pretty much all the different kinds of statements we're going to run into in this little section. And what we next want to do is determine whether they are true or false. So math people, they like to do this. They like to determine whether statements are true or false. So that's why we study statements, because they can be true or false. They are one or the other. And so math people like to determine which one they are. Sometimes it's obvious, and other times it's not obvious. So I'll write down another statement that's similar to the one I wrote above, and this one will be true. For any right triangle with side lengths A, B, and C, where C is the hypotenuse, A squared plus B squared equals C squared. So this statement is something that you have probably seen before. And this is just another example of why you have to consider the entirety of the statement when you read it, not just pieces. So this guy is a statement and it's true, it's called the Pythagorean theorem. But later, what we care more about is how to show it's true. Or prove it's true. And right now you're saying it's true just because you've heard that it's true and you've used it a million times. But that's not a proof of why it's true. Okay? So right now, we're going to start off with some things that we can show is true. Some stuff that's easier. So just as a little mini example here, what can you not do to reason why this is true? So this is saying that any right triangle you have will have side lengths A, B, and C obeying a squared plus b squared equals c squared. Now, I can't just try every triangle. Every right triangle. That would be impossible. I can't just say, okay, here's a right triangle. Yes, the equation works. Here's another right triangle. Yes, the equation works. Here's another one. Yes, it works. That's not proving that it's true. That's just saying that it works sometimes. And so proofs are wonderful because what they do is they show something always works without typically having to just go through all possibilities. Going through all possibilities is usually impossible. Okay, but let's look at some simpler examples where, for a different reason, you might be able to show it by going through all possibilities. Okay, so here is another example. There exists a number x. Solving the equation 3x plus 10 equals 4. Okay, so this is a statement because either there does exist such a number and it's true, or there doesn't exist such a number and it's false. It's one or the other. In this case, it's true, and we can actually show it by finding it. Or by solving the equation. So if you try to solve the equation, you'll get that x equals -2. So yes, there does exist such an x. So that's why it's true. And again, it's because the whole statement comes as a big one package. So it's not saying anything else other than that there has to exist a number solving the equation. So if you can find such a thing, then it's true. If not, it would have been false, if there was no such thing. Okay, so here is another one. For any pair of numbers, a and b, a squared plus b squared equals a plus b squared. Now what you might do is you might just look at the equation and say, aha, I've seen that before. In pre-calc, my professor told me never do that. That means this is false. And you would be lucky because the statement is false, but not just because of that, it's because you have to read the entire statement to see why it's false. Because if I change the words, I can make this true and still keep the equation the same. So be careful with that. So yes, this is false, But the key reason is this phrase for any, because what this is saying is that this equation will always work no matter what two numbers you pick. So why can I show that it's false? Or why can we see it's false? Well, it's because we can find something called a counterexample. So a counterexample is really just an example that shows a statement as false. So this can be done because the statement is trying to make a claim for any pair of numbers. And that means that for the statement to be true, it's got to always work for any pair of numbers. So if I can find a pair that don't work, what I'm saying is you're wrong. It doesn't always work because here's two where it doesn't work. Okay, so like if A equals 3 and B is 2, then I get 9 plus 4 equals 25. So that's my counterexample. And so that shows that this doesn't always work. Okay, so that's why it works. So this only works because the claim or the statement is that the equation a squared plus b squared equals a plus b squared will always hold. And we showed it doesn't. Okay, but change the words and you get a true statement. So you can't always just zoom in on the equation. Yes, you've seen that equation and you've heard your pre-calc teachers say don't do that, but you have to read the entirety of the statement to decide if it's true or false, not just look at the little mathy parts. Okay, so that's one big takeaway. Note, statements are often complicated you can't just sort of zoom in on the math. You have to read the whole thing. You have to understand the whole thing. And so for an example of why you have to do that, consider the following two statements. So, and then try to notice the difference. So here's the mini example. So one of these is what I just wrote. For any two, I'll just write it quicker. For any two numbers, a and b, a squared plus b squared equals a plus b squared. Okay, we already said that that was false. But let's compare it to the following statement. There exists two numbers, a and b, such that a squared plus b squared equals a plus b squared. This guy is true because it's a different statement. Still involves the same equation, but instead of claiming that it always works, it's just claiming that it works once, that there happens to be a pair of numbers where it works. And because the claim is just that it works once, we can actually show it or see it by giving an example. So if a equals 1 and b equals 0, then I'll get 1 squared plus 0 squared equals 1 squared. 1 equals 1. So that's why it's true. It's because now I'm claiming that it works once, that there exists two numbers that make it work, versus before I was trying to say it always works. So it's two different statements about the same equation. That's why you have to really read the entirety of the statement before you try to decide if it's true or false. You have to understand what the whole statement is saying. Okay. So now let's compare something a little bit differently, a little bit different. So you're going to keep seeing, again, these phrases, for any and there exists. They're very important. We'll study them more later, but I'm going to keep using them. For any number n, here's something that you've seen before. The derivative of x to the n, what's that rule again? You bring down the n, and then you subtract 1 from the power, I believe. Okay, so here's a statement. Now, this you've seen before, so you probably know it's true. The derivative of x to the n is, in fact, n times x to the n minus 1, and it does work for any number you put up there. So that's why it's true. But you can't show it as easily as we could show this other thing. So what's the difference? So what I'm saying is here, I showed that there exist two numbers making this equation work just by finding one. But that was because the claim was that it works once. Here, the claim is that it works always for any number. So I can't just show it by seeing that it works once. That's not enough. That's not proof. So like you could do this, you could say, okay, well, I know if the power is 1, it's going to work. And I know if the power is 2, it's going to work. But that doesn't mean it works for all the other ones. You still have to see why it works. And you don't want to try every single number because that's impossible. That's also not going to work. So the beauty of proofs is that you show this fact without having to actually try every number. But right now it's important for you to see that if a statement is being made that something always works, it's not enough just to see that it works a couple times. That doesn't mean it always works. Okay, so later on we'll deal with what you can actually do with things like this, and how to prove things. But for now, just think about the fact that showing that it works a couple times is not enough to say that it always works. Okay, so versus if the claim is a little bit different, but I say the same equation, there exists a number n such that this is true. Oops. That undo button not working. Okay, so there goes lag. Okay. N to the x n minus 1. So now this one is still true. They're both true, but this one I can actually show by finding an example where it works, because all I'm saying is that there does exist a time where it works. So true, we can show it, whereas before we couldn't show it. We can show it by doing one example. So you could, for example, you could calculate this derivative by doing the whole limit definition stuff. I don't want to do that in this class, but it would work out and you would get this as the answer. And that would be enough to prove that it works, that the claim, that the statement is true, but that's only because the statement is that there exists something that works. Versus over here, if I did that to show this works, that would not be enough to show it, because I still got to show it for all the other numbers. And I literally cannot just do every number separately. Okay. All right, so all of these statements we were talking about are sort of things that you either knew before, so maybe you remembered they were true, or you remember they were false. And so that helped us decide whether they were true or false. So you sort of already remembered this equation existing, and so you can use that to think about the statements that they're involved in. Same thing here, you already sort of remember the derivative rules, so you can use your previous knowledge to decide whether the entirety of the statement is true or false. But very often, and in fact, more interestingly, we like to look at things that we don't already know are true or false. So let's think of a statement like that. So here's one. For any positive number, so what I mean are whole numbers, so I'll just list what I mean. 1, 2, 3, and so on, like that. The formula n squared plus n plus 41 is a prime number. So this is probably something that you haven't seen before, but it is a statement because it's either true or false, because either this little formula does always create a prime number when you plug whole numbers in, or it doesn't. So it is true or false, one or the other, but we don't know automatically, just from memory, or from previous experience, whether it's true or false. And this is a very important example because it shows you why you can't just assume it works by establishing a pattern. So for example, over here, this thing, you could like try a few and see that it works, and just from memory, you know that this equation works. But that will fail you, that kind of thinking will fail you here. So we can try some numbers. So if I plug in 1, what's that, 43? That's prime. If I plug in 2, oops, what is that, 47? It's also a prime number. If I plug in 3, I think that's 53, right? It's also prime. So you start thinking, this seems to be a pretty good statement. Seems to be true. No matter what I plug in, it seems to be a prime number. But you'd be wrong. This is much sneakier. This displays exactly why trying a couple things is not enough to show that for any statement that something always works, that something is always true, if your claim is that it's always true. So if I try something else, try 41. So it would have taken me a long time to get to 41 if I started plugging everything in. But 41 will show us that it's actually false. Because, if you remember how factoring works, I can now take a 41 out. And this becomes 41 times 43. So this is not prime. Why is it not prime? Well, it's because it's two numbers multiplied together, and prime numbers have to have no factors, but this has two factors, 41 and 43. So this is not prime, as opposed to these numbers up here, which didn't have any factors besides themselves. So this shows the statement is false. So this is, again, it's a counterexample. So a counterexample can be made when you're trying to say that something always works, and it turns out it doesn't. Okay, so this is just all sorts of kinds of statements. We're going to try to stick to mathy statements because the English statements can get a bit trickier. We'll leave those to the logicians, I think, the linguists. So next time, we're going to narrow our focus. So we'll focus on one type of statement. And it's going to be called a conditional statement. So the statements we looked at so far are sort of all over the place. And the main thing to summarize from today is that statements must be either true or false. And I'm often going to write T or F because I don't want to write the whole words every time. And you have to read the entire statement not just the equation to understand it. And just because an equation holds a few times, or it doesn't have to be an equation, but something, doesn't mean it always holds. So, although seeing that it holds sometimes might give you an idea that it holds all the time, you cannot use that as evidence, as an actual proof that it does. And it also tells you that you have to look at the entire statement, not just the something. If the entire statement is claiming that it's always true, like here, then you can't just try stuff to see if it's true or not, but maybe you can find a counterexample to show it's not true. But if I change the phrasing to there exists a whole number that's, where this thing happens, then suddenly it could become true because now the claim about the something is different. The claim is that it just works at least once, and it does. If I plug in 1, then I'll get 43, which is prime. Okay, so that's going to be it for today. See you next time.